So I've got some notes set up here. Essentially, this is how you would go about calculating a confidence interval for just a single piece of data to calculate, say, a mean. And the generic formula is this one here. The confidence interval, it could be a 90, a 95 or whatever, is X bar plus or minus a magic number, a t-score, times the standard error of X bar. And now this magic number is a little bit difficult when you do means because it actually depends on two different things. This number depends on how big your data is. Have you got 50 numbers in it or 500? And it also depends on whether you're going to find these three things. So that number varies a lot. In a proportion question, that number would be fixed. For instance, if I wanted to get a 95% confidence interval, that number would be 1.96. And it doesn't matter the size of the data when it's proportion, that number doesn't change. So that's the first difference, that this magic multiplier will be different depending on size of data, which becomes degrees of freedom, which is how much is in a data takeaway 1. It's an extra little twist. And whether it's a 90 or a 95 or whatever you want. On the other hand, the standard error of a single mean is just the standard deviation divided by the square root n. So I'm going to do one question by hand. Well, mostly by hand, it'll really be calculator and solve. And then we're going to show you how you're really going to do it in kind of real statistics life. You're going to use a software package. In our case, it's going to be Solve. So let's have a story for this. In my example, scientist wanted to know the mean number, or as we would probably call it, the average weight of an adult elephant. So I guess that scientist would probably be a zoologist. So maybe he's doing a PhD on elephants and he wants to find out what the average weight of, say, an adult African elephant was. So what he would do if he was Bill Gates is he would go to Africa, find every elephant, pick the adults and weigh them all. And if he did that, he'd be pretty stupid, but he would get the correct answer. That would be a census. But we know that's just not reasonable. You're not going to do that. So what he did instead is he got a sample of 133 elephants. And he found out that their average weight, God, this is a guess. I don't know what an elephant weighs. Can we pretend I did? And it was 890 pounds. And the standard deviation of the sample was 100 pounds. And in particular, he wants to find a 99% confidence interval. So that's kind of my story. So we are going to take this information and we are going to find a 99% confidence interval. And we're going to do most of it by hand. And then I'm going to do the same question on salt. Hopefully show you that you get the same answer. barring rounding off. Oh, and he wants to find it to 1 decimal place. So that's the formula I'm going to use. So to get a 99% confidence interval, it's going to be the mean plus or minus that guy. When you know the confidence interval, you sometimes change the notation a little bit. And you write that. So do you see my generic T has now turned into a T 9.99 because it was a 99%. Now I need to find the standard error. And the standard error is the standard deviation divided by the square root of n, which in this case is 100 divided by the square root of 133. So I'll go to my calculator and I'll find out what 100 divided by the square root of 133. And there's a couple of questions in your homework where you're actually asked to do that, just find the standard error. So in this case, to 1 decimal place, it's about 8.7. Now, I also need to find this fella here. Now, to do that, I'm going to use salt. I could use a table of values, but the table of values are very inaccurate because that piece of paper, that table that we've got, has big gaps in it, and you have to do guesstimates because of that. So let me show you how I would find the magic number for 99%. Okay. So you tick the salt button, and you'd have this guy, which is good. In this case, you do a mean is 0, a standard deviation 1, and the sample size in this case was 133. Now, I know that this story has elephants and X bar is 890 and all that. Don't do that. All we're using this is for one very minor job. We're trying to find the t-score for a 99% confidence interval. So when that's the case, you make this 0, you make that 1, you do a confidence interval. And you put in, what was it, 99, and you do a generate result. And I made the mistake because I'm, wait a minute, have I? No, 0.226. I thought I'd made a mistake. That is a mistake. I know that's wrong. Reset. Kick out of there. Oh, I know what's happened. The salt button I hit was for a question. And what this software does, unfortunately, is it doesn't give you access to the guy you want. I mean, for instance, if I hit this salt button here, it would only be useful for this question. It doesn't allow me to get in. So I'm going to have to go back and go into 11A. It's a bit of a pain, but I can do it. And find the one where they asked us. Do you see it here? And I have to hit that salt button. That's a real pain in the button. Okay, so let's do T distribution, both tails. Degrees of freedom then is 132. And there's the number I want, 1.9781. That's a bit of a So the correct number is 1.9781. It's a little bit annoying that it does that, that you can't just use any salt button for any question. It restricts what you get when you hit a salt button to whatever you need for that one question that the salt button is in. But anyway, we got it. It's 1.9781, and now we can return. Now, you know you're going to be doing these questions all in salt, so it isn't so much jumping around as I'm doing for this question. So we've got all the pieces. We know X bar, it's 890. We know this guy, 1.9781. We know this guy, 8.7. And so we have 890 plus or minus what you get when you multiply those two together. So 1.9781 times 8.7. And I get the answer 17.2. If you take that away, you get 872.8. And if you add it, you get 907.2. And there is our 99% confidence interval. So we are 99% sure that the true value for the average weight of these elephants is somewhere in that range. Right. Unfortunately, finding that number was a bit of a pain because I had to leave 11B and go into 11A so I could hit the salt button that would let you find this guy. Now, let's show you how you would probably really do this, and this is how you would do it in virtually all your homework, is same question, but using salt. So I'm now going to go back to salt. We're going to go into 11B, so I'll make that set up. Good, right. So this is how you do that same question in salt. Right. This guy is set up for the same kind of question, so use salt. One sample T, make sure you're in one sample T distribution. The mean is 890 for these elephants. The standard deviation is the standard error, I should say. Oh no, the sample standard deviation. I only need to put in 100 here. It's the sample standard deviation. The sample size was 133 elephants. So, average elephant in my sample 890, standard deviation of my sample 100, not the standard error, just standard deviation, and the sample size. So that's the three numbers that you got in the story. Hit that guy, make this 99. Now I'm going to hit generate results. And when I hit generate results, I want the answer to be 872.8 to 907.2. Do you know it probably won't be? But it'll be darn close to it because there's a bit of rounding off, you know, that they did. And because of that, we sometimes disagree. And it is 882. Actually, that's a bit out. And 897. What happened? Standard error.
Your sample size is 1100. I don't know if that's changing it.
Oh God, yes. Did you see I typed in sample size 1133? I had one too many. Let's do it again. Now 867.3 and 912. That's a bit better. Not great. Why is that so far out? I don't know. Standard error 8.67. That is bang on. Degrees of freedom fine. That guy, that guy. That is about 5 out, and this is about 5 out. That's quite a lot, but 5 out of 867 is only about 1% out. So I'm pretty sure if I did everything to like 6 decimal places and only rounded off at the end, we would be fine. So what am I meaning? Do you see that 8.6711 guy? I'll show you what I mean. If I had used, instead of that number, 8.6711, now you might think there's not a lot of difference. Well, that lot of difference eventually made a big difference in the answer. If you're given a question and they tell you to round off to 1 decimal place, it's a good idea not to round off any of your calculations to 1 decimal place at all. Do the entire calculation to 6 or 7 decimal places and only round off the final answer to 1 decimal place. And that will probably make this answer, although it doesn't look like it's a major issue, it would probably be the difference between why I'm 5 out. Can you imagine that extra 0.03 making a difference when you merge it with other numbers? Right. It adds to the problem. So I kind of expected that would be a little bit disappointed it was as much as 5, but it's still the correct method. So we can trust SALT because it's done by a computer, and computers, at least when they do number crunching, are pretty reliable. So what's the rest of today going to look like? Well, the first part of today is we are going to look at some homework questions, and we're going to show you essentially how you use SALT to do almost all of them. So, question 1, in each of these, find a particular confidence interval. They're all the same kind of question. Anybody got a preference, A, B, or C? I'm only going to do one of them. Any preference?
We can't see them.
Oh, can you see it now?
No.
Let's try again. There, can you see it now?
Yes.
Yeah, I had to go back out and back in. Okay, we're good. Right, do you want A, B, or C? They're pretty standard questions. They're not any real frills. They don't even give you a story.
How about B?
B is pretty good. Okay, well, that might help you see it a bit better, right? So I'm just taking a note of these because when I hit that, it disappears. In B, the mean is 79. The sample standard deviation is 12. And the confidence interval that they want me to find is 90%. So I'm going to hit the SALT button. Are you seeing the SALT button? Okay, good. 1 sample T, right place. The mean is 79. The sample standard deviation was 12. So basically, I'm just using the numbers that they gave me. And there was a blinking sample size I should have written down. And I knew I should have done that, and I didn't. So I'm going to have to go back in again. And do you notice what they do? They change the blinking question. Okay, this guy's going to go here for a second. There. Okay, in the new question, right? Because now that I went out and then I had to change, it changes every time. The new mean is now 77. The standard deviation, it's now changed to 5. And the third number I should have kept track of, which I didn't write down, was 12. Confidence interval, I believe they wanted a 90. So when we hit generate results, the 2 numbers we're interested in is the lower limit is 74.4 and the upper limit is 79.6 roughly. You see that basically these two are your confidence intervals. Right. So you put in mean, standard deviation of sample, and sample size, and SALT will just be your friend and do all the other stuff for you. So let's close those windows and bring
I have a
this one
question.
back. Yes,
What homework assignment is this that you're currently on?
this is 11B.
Okay, thank you.
So can you imagine doing the other two questions using SALT pretty much the same way? Probably take you a couple of minutes each, nothing too scary. Do you see that there's another batch of 4 more where you do essentially the same again? Do you want me to do another one of these, or can we skip by these guys?
Could you
Skip
do
by
one
'em?
more?
Okay, we can do one more. I'm going to have to move the guy, so I'm picking C. So I'm writing these numbers down. It's 102, 16, 81, and a 99% confidence interval. Okay, now I have to move this guy over here, because when I hit the SALT button, it appears here. And the mean is 102. The standard deviation of the sample is 16. The sample size was 81. Confidence interval 99. And then when I hit generate results, these two numbers are your 99% confidence interval. So we're 99% confident that somewhere between 97.3 and 106.7, the real answer is. We're cool with that process. Does it look pretty straightforward? As long as you tell me the 3 guys I need, the mean, the standard deviation of the sample, and what kind of confidence interval number that you're looking for, then we are pretty much good to go. Now, this one's still using SALT, but they're asking for other things. At the age of first marriage, right, so they did a sample of 81 women who graduated from college in 1990. Kind of thing social scientists do. And then they do the same thing in the year 2000, and then the year 2010, and then they do it the year 2020. And what they're doing is taking little snapshots of society. And there's many things you can look at society, but here's one, age of first marriage. I actually know some data on this, not this particular set of numbers. But in the last, what would you call that? In the last 30 years, do you think the age in which you get married, right, a woman or a man, it doesn't matter, the data is about the same. Do you think it's changed over that 30-year period? Have people get married later in life, about the same as they did in 1990? Or are they getting younger when they first get married? Does anybody have a gut feeling about which of those 3 is true? Because I do know.
I think they got later.
They did. The age at which women got married has been increasing steadily since about 1960. And there's lots of reasons behind that, because once they discover something that's interesting, social scientists then try and say why, or try and find why. Do you know the 3 main reasons why women are getting married later in life?
They go to college, they enter work, and I can't remember the third.
Right. And the third one is actually much better birth control methods. So it allows them to it used to be if you got pregnant, you ended up getting married, right? So if you didn't get pregnant, there was less demand on that social thing. That's probably not true today anyway, but it certainly would have been true in the 60s and the 70s. So a large proportion of people. So back to this question. What do we have then? Well, we have 81 women, we have a mean, and we have a standard deviation. But they want us to find the standard error. And you might think, oh, is that going to mean we do anything different? No. I'm just writing these numbers down because they're going to disappear in a second. I've got a mean, I get a sample size, and I've got a standard deviation. And I'm going to click on this question. Oops, I'm going to move it over here. Almost did that mistake again. I'm going to click on this question, and I'm going to put in a mean of 25.4 and a standard deviation of 5.4 and a sample size of 81. And then I'm going to go down to confidence interval. And you're going to say, but they never mentioned anything about confidence interval. They never said 90 or 95 or 99 or any other number. But I still need to put a number in there. Why does it not matter what confidence interval number I use?
Because the standard error is going to remain the same.
Exactly. So pick your favorite number. I'm picking 95 because I'm lazy. It means I don't need to change anything. And the standard error is 0.6. Are we cool on that? That you can use salt just to get the standard error? All you do is pick a confidence interval. If you don't like picking one, use the 95 that's already there. If I change, let's just convince you that that's true. Suppose I change that to 99. Now notice standard error was 0.6. Do you see the standard error is still 0.6? The standard error does not change. It's a fixed number like X bar, right? The sample mean is fixed, right? It doesn't change if you choose to do a different confidence interval. So that was kind of interesting. So we would be putting in here, I think it was 0.6, 0.6. And then they say, write a sentence that interprets the value. And I'm just going to let you read over that and figure out what that guy is. And then they do a 95% confidence interval. So I'm not doing this, but couldn't I go back there, hit salt and go through it, and this time read off the lower and the upper value, and that would be my confidence interval. So it wouldn't change. And a little sentence about what does this mean. Shrink this back a little bit. Volunteers who developed a cold in the previous 24 hours were randomized to take either a zinc or a placebo every 2 to 3 hours until their cold symptoms were gone. 25 participants took the thing. (23) took the placebo. The mean overall duration of symptoms for zinc loss age group was 4 days. Standard deviation was 1.4. For the placebo group, it was 7.2, and the standard deviation is 1.2. Now, let's go out of here and tell you what makes this question just a little bit different. There's actually two groups. The people who got the placebo pill and those who got the zinc. And we are going to get a 99% confidence interval of this group. And won't you just plug those numbers into salt and get your answer? And then you're going to do it later on, if they wanted to, because some people get the other question. You could get this one to do, right? Because some homework, do you know how the homework question is randomized? Some of you would be doing this one, others would be doing that one. Wouldn't it simply just be going into salt, right? Plugging in the numbers and getting the answer. I won't do this answer, but can I pretend that for the zinc, the average number of days it took was 3 to 5. And for the placebo, the average number it took was 6 to 7. Can we just pretend that if you took a zinc tablet, you'd have the cold for 3 to 5 days before you were better. And if you just took the placebo, it would take you 6 to 7 days. Now, when you look at these two intervals, do you notice something very interesting about them? They do not overlap, do they? So couldn't you use this as evidence that zinc actually reduces the amount of time you'll have a cold for? Now, if this data was valid and true, you could advertise your zinc pill as, hey, have you got a cold? Do you want to get rid of your cold? Take Zinco. It will half the time that it takes you to recover, right? Or whatever. If you've seen those kind of adverts where they ask you to take stuff, right? Now, zinc is actually very good for the immune system. So I wouldn't be surprised if actually zinc in its various commercial forms, right, when you take a zinc supplement, isn't actually good for you. So I would like that one. I wouldn't knock that one too much. I think there's pretty good data that zinc is. Do you know that there's another thing that some people take to either prevent cold or to reduce it, where there's, as far as I know, there's no good scientific evidence to prove that it actually works? It's a vitamin or a vitamin, whatever Americans pronounce it as. Do you know what vitamin I'm talking about?
Vitamin C.
Yeah. There's no good statistical evidence I've seen that says vitamin C helps you not get the cold or reduce. Any evidence I've seen on it is that the placebo effect is true. If you take vitamin C after a cold, your cold might last 1 day less than it would have. Not because the vitamin C is doing anything, but because you're believing it strongly enough. You're, a lot of your body is your brain can do an awful lot for your health. And if you're convinced something's going to do you good, it can have that positive effect. It might make your brain, make your immune system work harder because you think, yeah, I'm getting rid of this cold. Let's get a move on. Let's get this, right? Whatever. But it's true. A lot of supplements that you read about have no evidence that they work. Do you know what they are normally all categorized as to keep them out of the FDA? Because the FDA won't let you do something unless you can prove it, right?
Supplements.
Yeah, they call them food supplements, which is basically just another word for food. You're just eating it like you'd eat a carrot, right? It's just concentrated carrot or whatever. So don't spend your money on them. There are a few exceptions, as I've said, and I don't have money in zinc companies, but zinc has been shown to be a good, of good benefit. Iron is good. So if you take an iron supplement, there's pretty good evidence that it does help with anemia and some other issues. But most of the others are just rubbish. You're just spending money. Do you know what your body does with most of them? If you take a vitamin C or anything, it totally does nothing to it. You just pee it back out again. That's all you do with it. So I'm writing on here. I shouldn't be doing that. Okay, I apologize, but it was interesting. So it got me thinking. Right, let's get a move on with these questions then. Question 5 are yes, no's. Is it correct? Is it not? This one here is basically use salt. Except
There
it
isn't a
doesn't have it.
salt.
There isn't a salt button. And I can now tell you how this doesn't have a salt button. And it's this darn word or words. If you're being asked to find an approximate confidence interval, and actually I wrote that down in my notes, so let me show you. If you're asked to find an approximate confidence interval, they are telling you that this guy is to be 2. So a 95% confidence interval, use 2. Did I write that in my notes? I think I did, didn't I? Oh, I apologize. Oh, here we go. My other notes. This is for the next section. So if you ever see approximate 95% confidence, use 2. Okay, so that's just a little note to self. There isn't a salt button. What the heck have I to do? It's probably going to be one of these, use 2. So if that is the case, do you see that I now would have to do it by hand? Right, so the question I gave you at the start of today, X bar plus or minus 2 times the standard error. And that would get you the answer you're looking for. This one here is a pretty standard one. And this one here.
We can't see the screen again.
Oh, let's go back. The last 2 questions are basically back to doing what you've normally been asked to do. Right, so here are some data. Find the standard error and confidence interval. Here is some more data. Find the standard error and the confidence interval. And these guys here says using the approximation that is appropriate for large samples. Okay. Now, when it's a 95%, what do you use for T? We just mentioned it a minute ago.
2.
2. Do you know you can also use 1.96? Remember the Z-score?
Yeah.
What would you do if it was 90%? What would you use as your T value?
1.65.
Yep. And if it's 99%, what should you use?
2.58.
Yeah. So those are just things you've got in little cheat cards. And aren't they the magic Z-scores? So when you look at the situation that we're talking about, these T distribution things, there are some interesting properties. When N is large, what the heck does that mean? It roughly means if it's more than 1,000. The magic score for 90, for 99, I should have said 95 before that, and for 99 are the same numbers for the Z-scores. Remember the Z-score? And those were the 3 numbers people just mentioned a moment ago: 1.645, 1.96, and finally 2.58. Now, the one they did that used the word approximate is this guy. And you say, well, what's the difference? Well, not a lot. Would you agree that 1.96 and 2 are darn close to each other? And if you rounded off your answer, you'd get the same number. So it's not that approximate is a different story. It's basically just this number rounded off to 2. And the approximate means you rounded it off to 2. Right. If I was going to do an approximate 99, not that there is a homework question like that, wouldn't I probably use 2.6? And if I wanted to do an approximate 90%, wouldn't I probably use a 1.6? If I do large values, then try and use these ones that are a little bit more accurate. Now, before we finish this and start our last section, let's talk about the properties that need to be true. So what needs to be true? To be allowed or to be valid to find confidence intervals. Here is our first rule. The population needs to be roughly symmetric. So if you had the population, it has to look like a bell, right? It can be, and it is okay to be a little bit skewed. It can be, and it's okay to have two little bumps, but there's a fair amount. That's why we're using a vague word called roughly symmetric. Don't try and do estimates of a single mean if your data, for instance, is clearly binormal, right? In other words, it's got two bumps in it, right, bimodal. Why would it be a bad idea to try and find a single sample from data that looked like this? Well, this is really probably two separate populations mixed. Can you imagine you did adult Americans? Wouldn't that have a bump for the males and a bump for the females? And it's not got a nice hill shape. So you'll get an answer, but the chances are that it is very problematic whether it's any good, right? 2, size. Talked about this last time. You need about at least 30. Right, so you're pushing your luck if your sample is less than 30. All sorts of bad things can happen. You want the data to be independent of each other, right? So if you're measuring people's weights, isn't it a bad idea to measure people from the same family? Because, you know, some families are skinny and some families aren't, right? And if you're picking 5 people from the same family, they're not independent of each other. Oh, and an obvious one that I almost forgot, and it's an unbiased sample. Right, so don't go to a gym and measure people's weights, because people who go to the gym might not be the same as the general population, right? Don't
Can you
pick.
move your paper up a bit,
Oh,
please?
so yeah, don't pick 20-year-olds. If you want the entire adult population, and make sure that you've got young and old and healthy and not healthy and everything in between, to make it a fair representation of the population. So unbiased sample is what we're covering. Independent is connected to that in a way, because you could group those two together. Because if the data isn't independent, then it won't be unbiased, right? There'll be a problem with it. Any questions about calculating? As you noticed, it's mostly SALT with a few amendments based on what we are told. Any questions about it? We move on to the last one. Okay, I'm seeing nods, so I like nods. Here's our next section. Give me a few moments to load up our last guy. It's a very small section. There are only 6 questions in it. So hopefully it won't take us too long, but for those who like to write notes, I'll give you time to write those down. Brad, what's the difference between an elephant and a loaf of bread?
I was gonna say the ivory, but I don't know.
Oh, well, then I'd never send you to the shop for a loaf of bread. No. Jade. Why did the Canadian cross the road?
Why?
Because they saw an American do it first.
Oh, wow.
I don't know what kind of oh wow that is. Is that joke that bad? It's an oh wow joke. Okay. I think, oh, we got some chat, so maybe we've got something I should do. Oh, some people are answering. Okay, I got you, Sydney. I should keep the chat open because if you say anything, Sydney, I'll be able to tell what you're asking or saying. Okay, everyone, let's look at how do you find confidence intervals for the difference between two means? Well, it has a very similar formula. You find the difference between the two samples, means, the X1 bar and the X2 they're called. You find this magic t-score thing, and then you get the standard error of X1 bar take away X2 bar. Now, this standard error can be calculated typically in two different ways. The one that we are going to be doing, and this is the general one that gets used vast majority of the time, is this one. So the standard error of the difference between two sample means is the square root of this guy. In fact, if I cover this guy up and you tidy it up, isn't it the same as S over square root of n? So it is just like the first one. But because you're adding them together, you kind of stick them together. So that's why they're a square here and the two things are added. And that's the formula for the standard error for the difference between two means. Now, if they ask you to compute an approximate one, you'll use 2. If the data is large, won't you use the 1.96 or the 2.58, depending on what we've got? Now, the last thing is, they didn't, or at least I don't think they did, ever ask you to do it, but if they say the data has been pulled, then the standard error of the difference is S of P times this ugly square root. And S of P is the pooled standard deviation. You will recognize that question because it'll stick out like a sore thumb. It will tell you a story about two different populations and two samples from those, and they pulled the data, and the pooled standard deviation was 22. There'll just be one standard deviation, the pooled one. I don't like pooled data for the same reason I don't like it when it's proportioned, but it can be useful at times, so it's there. Now, what's a little bit different about this compared to all the other situations is that these questions really are too difficult to do by hand. Not that I couldn't do this piece by hand, which I could, but this fella here, the magic t-score, is very complicated to calculate. They do actually have in the book a big ugly formula that's about this big. Nobody in their right mind would ever use it. And since you need to know this guy just to get the t-score, it would be, we basically just say, okay, we're going to let Salt do it all for us. So you're not going to see me doing one by hand stroke calculator and then do everything else by Salt. They're all going to be done by Salt because they're just so ugly. So let's get started. We have our first question, I hope. Are you looking at question 1?
Yes.
Right. Now, I said Salt, and there is a Salt button there. But let's not worry about the Salt button because
We
here,
are looking at it.
I can't see it.
you can't. Let me check it again. And I probably clicked on the wrong one. There, can you see it now?
Yes.
Right. This is a story about testosterone levels in men, although women actually have testosterone. Did you know that, women, that you have testosterone?
Estrogen turns to
It-
testosterone.
So, useless piece of information, but I thought I'd tell you that. So the researchers suggest that there are occupational differences in this level. Medical doctors and university professors were two of the occupation groups for which the mean and standard deviation were given, and they did a dot plot and they did some other stuff. So they were kind of interested in this, what would the levels look like? Computer output for a 95% confidence interval. So basically, this isn't salt, but there are lots of software out there that do the same thing. So if we look at this data, we can pretty much tell what we need to know. Can you see that the doctor's sample was 16, that their mean was 11.7, their standard deviation was this guy, and the standard error, if you just did these guys on their own, would be that number. If you did the professors, there's only 10 of them, it would be this number. The difference between the two is 0.6. Well, that would be easy. Couldn't you just take this number and subtract that number and you'd figure that out yourself at 0.9, I should say. There is the 99% confidence interval. And a little guy down here called degrees of freedom 22. So everything and stuff you don't need to know is in this list. First thing, 95% confidence interval is given as these two numbers, which it is. The unpooled procedure, well, that's good because we don't like pooled, uses which one of these formulas?
Is it the first?
Yes. If they had said the pooled procedure, wouldn't you use that one?
Yes.
Right. So that's all that question is right. Now, identify numerical values of these things. Note degrees of freedom is given as 22. Okay. Round your standard error in your multiplier to 2 decimal places. Statistic, standard error, multiplier. The statistic is the difference, so that's 0.9. The standard error is, oh, well, interesting. The standard error is not given. How am I going to get the standard error then?
We use the formula.
We could. And the formula would be that x square root s1 squared. I'm going to hit salt button, see if we can cheat. That's the right word, cheat. Now, little darlings. Oh, I should have moved that too late. Okay, here's a new set of numbers, but that's fine. It's the same story, but different set of numbers. So if you know the standard error of these two guys, I should say the standard deviation of these two guys, we can calculate the standard error of x1 bar, take away x2 bar. And since I couldn't use that salt button because it wasn't set up the way I need it to be, although I've got a feeling I could fix it. The formula we're going to use is this one. So you can't see it anymore, but this guy was 3.33 and the sample was 16. And this second guy was 2.56 and the sample size was 10. So I'd go over here. And I do the square root of 3.33 squared divided by 16 plus 2.56 squared divided by 10, and I get the answer 1.161 to whatever degree they want. So I could eventually get that guy. Now, if you wanted to fill in the other numbers, because they had three things. One of them was called the statistic, which is basically the difference between the two. The second one was called the standard error, and we actually just found that guy. And then they've got a thing called the multiplier. And the multiplier is in fact that guy. And they told me that the degrees of freedom are 22. So I'm going to see if I can cheat. Darn it, space, excuse me. You notice I didn't swear there. If I hit salt and I have my window in the wrong place, it rubs out the question. And so when I go back in, it gives me a different question, which is a real pain in the butt. There, I got it now. Okay. And I should have closed the window and showed you what I'm looking at. So we now need to find a magic t-score for, say, 90%. T-distribution, degrees of freedom 22. Make sure you make that a between. And then make this guy, I think it was 95%. And the number you're going to use is that guy. So I used the same technique that we used a way back when we did 11A. Do you know when you had to find a magic t-score? You would go into t-distribution, you'd put in degrees of freedom, you'd make this guy between, and then you'd make this number. If I wanted the 99 one, it would be 2.8. If I wanted the 90 degree one, it would be 1.71. And that's how you get the magic t-score. So it's all done essentially using salt or a calculator. And now we are looking at more standard question. This one is a story about taking zinc and not taking zinc. And there's a group that took zinc. Let's see. Volunteers who developed a cold within the previous 24 hours were randomized to take either a zinc or placebo until they were gone. 25 took a zinc, 23 took the placebo. Oh, they've changed the order. For the placebo group, so I'm writing this down. For the placebo group, the mean number of days was 8. The standard deviation was 1.4. And for the placebo group, there were 23 participants. And then for the zinc group, the mean here was 4.2 days. The standard deviation was 1.4. Oh, same number. And there were 25 of those. So before we start hitting zinc, let me show you what we've got. This is basically a summary of that question too. Placebo group took 8 days. This is their standard deviation. That's how many were in the group. Zinc We'll call them group 2 now. This, and this. And we are going to use salt to find eventually a 95% confidence interval, right? So now that I've got all my numbers handy, let's do it on salt. Here we go. Can you see salt? Is that you on the salt page? Right.
Yes.
Now, which one of these guys should I be using for a 95% confidence interval for the difference between two means?
2 sample T.
Where is it? 2 sample T. There we go. Now, the first group are the placebo group. So that's going to be an 8 for the average number of days, a 1.4 for the standard deviation, and the sample size here is 23. And for the people who took zinc, it was 4.2 days to get better. It was 1.4, and it was 25. And we do a confidence interval. And down here, we do a 90, oh, it is 95%. So I should be able to generate all the numbers that we want. And the most likely numbers that you're going to be asked to fill in are these guys here. So the difference between them is 3.8. The lower number is 2.98. The upper number is that. Do you see the degrees of freedom is a weird calculation now? It doesn't even bear, it's not size of data takeaway 1. Do you see how weird it looks? That's why you can't really calculate it anymore. And our standard error. I'm going to write down the interval. I'm just going to call it 2.99 to 2 decimal places and 4.61. And they do ask you for other things, but I'm just going to look at that one snapshot, one of the more important ones. Right. So we are 95% confident that the difference between these two groups is somewhere about what, 3 to 4.5 days? Now, do you notice that all these numbers are positive? This happened when we did proportions. If all these numbers are positive, it means they're greater than or equal to 0, right? Now, if you do a little bit of math here, not really big math, doesn't that make the first group a bigger number than the second group? So haven't I got evidence that zinc actually does help? People who don't take zinc have the cold for longer. How much longer? Well, something like 3 days longer, at least 3 days longer, right? Could be as much as 4.5 days longer. Now, what would happen in a different question if the numbers were all negative? What would be the conclusion you could make this time? What do you know about the difference between them then? Less than 0. And if the difference is less than 0, doesn't that mean the first guy is less than the second guy? That makes sense. That if the difference between them is a negative number, right, it's guaranteed to be some kind of negative number, doesn't that make the first thing smaller than the second? Small thing, take away bigger thing, gives you a negative answer. So you could use this interval as proof that the first population has a smaller average than the second population. And what happens when it contains 0? Well, when it contains 0, we don't have any real evidence to say that one of them is any bigger or less than the other, right? Could be either. Can you remember there was a similar result when you did the difference between two population proportions? If the interval was always positive, the first guy was bigger than the second. If the interval was only negative numbers in it, the first guy was less than the second. And if it contained 0, you couldn't tell the difference between the two. Any questions about that? Are we good? Does it make sense that a positive interval means that the first thing is bigger than the second? And that numbers that are negative intervals mean that the first thing is less than the second? That's essentially the gist of what I said. Okay. Then, oh, darn it, in space, where's my windows? Go away, Salt. There we go. Okay. Let's see if you're seeing the right guy now. We only have a few more questions and we are pretty much covered. Now in question 4, well, are you looking at question 4 first? Yeah. Right. In question 4, this is our story. Each of 63 students in a statistic class used their non-dominant hand to print as many letters of the alphabet in order as they could in 15 seconds. What a cruel thing to do. Okay. The following output for this exercise gives the results for a 95% confidence interval for the difference in population means for males and females, and it's an unpooled procedure, which I like, right? So if this data is valid, females could do about, on average, 12.6 letters of the alphabet, and males, because they're just competitive or whatever, they did about 1 letter more. You probably could read the females, you probably couldn't read the males. Look like a chicken scroll. Right, there's the standard deviation. It's basically the same numbers as, or the same format as question 1. Do you see it's got the same software they probably used? But everything we need is here. We just have to treat it the same way that we did question 1, because you see there's no salt button. So that means it's either numbers that we can read straight off the thing, or later on, if we have to, we could do other things. So what's the difference with, what was the mean number of letters printed by females? 12.655. Right, I'm getting that straight out of here. For the males, it was 13.702. And I'm getting that straight out there, right? Didn't need salt to do that. What's the difference between them? It's that number there. Oh, good, it worked. What is the 95% confidence interval? Well, isn't it between that number and that number? So the lower limit would be -3 and a bit. And the upper would be this number. Pick a sentence that basically tells you that. Yes?
Wouldn't it be like the 1.058 as the upper limit?
Did I? What one did I just copy? Oh, I copied the wrong one, didn't I? The heck did I copy? Whatever one I copied, it was the wrong one. You're right.
You copied the p-value.
Oh, okay, that's what I did. Write a little sentence, you know, pick one of them that tells you what you're doing. Now, do you see this interval goes from -3 and a bit to 1 and a bit? You know, when I draw my little funny brackety things, can you see that that one is -3 and a bit to 1 and a bit? It's just what the thing looks like. Are you comfortable with from -3.1 to 1 and a bit? That's about -3 point. Well, actually, if you put your thing over it, it tells you it is. Now, what can we tell from this 95% confidence interval? What conclusion can we do? Well, do you notice that this interval has negative all the way through 0 up to 1? Doesn't it contain 0?
Yes.
And because it contains 0, doesn't that mean that there's no evidence to prove that one of them is bigger or less than the other? If they were all positive, it would mean the first was bigger than the second. If they were all negative, you know, whatever, it would be the opposite of what I just said. So we're looking for a sentence that basically says, since the interval contains 0, we cannot say for the population represented by this sample whether on average there is a difference between them. Right. So there was a little difference, about one word, but that is within the normal variation that you would get when you take any couple of samples. Right. Unconnected to this question, I wouldn't even publish this. Not that it's not that interesting, because it probably isn't to most people. But why shouldn't I publish this? Because it broke one of the rules that I mentioned earlier today.
Because the confidence interval is no good.
Yeah, why is the confidence interval no good?
Sample sizes are small.
Yeah, wasn't one of them 29? And it broke my 30 rule. Now, I can understand why they pushed it. Because together there's more than 60. You know, so the 34 kind of compensated for the 29, and it's not like a legal rule, you know, that you'll end up in jail if you use a sample size of 29 or 28. But, you know, when you start pushing that envelope a little bit, you're getting to the place where you should start to feel uncomfortable about conclusions. Now, this one was good. There wasn't any conclusion, but I would be worried if the conclusion was, oh, men can do it better than women. Because you can imagine some paper out there where they say, see, I told you, men are just better than women. They can even write with a wrong non-dominant hand, more letters than women, and a whole load of nonsense like that. You would be surprised by the number of people, side issue, but it's still valid. If you are doing a study and you want something to be true because your political viewpoint or your moral viewpoint or your world view or whatever it is that corrupts your brain, right? If you want it to be true, couldn't I just keep doing samples over and over and over again until eventually I got one that said what I was hoping to be true? And all I publish is the one that worked. And I don't tell you about the other 820 that I tried that totally disproved what I was interested in proving. And that is totally wrong in the scientific world. Does it happen? Unfortunately, yes. How does it get found out? If someone published a paper, other people would say, oh, that is interesting. I think I will repeat the experiment myself and see if I can duplicate the results. Typically, it's called duplicating data. So you duplicate the data. Now, can you imagine what's going to happen? 20 people in different parts of the world said, we tried it and we couldn't find any evidence that men were better than women as far as left and right-handedness went. And that person would then be looked at on the scientific world as a dubious source. So the next time they do something, people are going to say, yeah, isn't that guy that thought women were different than men as far as handedness go? That one was shot down in flames. How did he figure, I don't trust that guy anymore. So it's your reputation that's online. But if you don't care about your reputation, I guess it doesn't matter, does it? So, are we cool with that little side issue? What's the moral of that story? If someone tells you something, will you double check it or look for other sources that have said, we have done it and verified it? If a coffee company advertises a new paper that says coffee reduces your blood pressure, will you take that evidence with a pinch of salt? Will you be a little bit skeptical about it, right? It's a coffee company. Aren't they going to publicize good stuff? Do you think they're going to publicize reports that say coffee's bad for you? Right? No, I doubt it. Right. Okay, we got 2 questions to go and we're out of here. For a sample of 35 men, the mean circumference is 56 and a standard deviation 2.9. For a sample of 35 women, the mean head circumference and the standard deviation 2.1. Find the values for the difference between them. Find the standard error and approximate. Okay, this guy has no salt button. So let's show you how we would do that guy. So group 1, which I'm going to call the men. Sample size, 35, okay. The mean head circumference, because they've got big heads, is 56. And the standard deviation was 2.9. The second group, which is women, in this case, the number in that sample was 35 as well. The mean was 54, and the standard deviation was 2.1. And in a few minutes, we're going to calculate the standard error, the difference, and then the approximate 95% confidence interval. If you look at the average circumference, men have got bigger heads than women. Do you think that difference is significant statistically? Do you think 2 centimeters based on this information, do you think it's going to make it?
Probably not.
Yeah, I don't think so. I mean, it's only 35 people. Don't you only need a couple of guys who've got really big heads and that would do it? Right, or a couple of women who've got very small heads. Very, doesn't need to be hugely small, but just enough to make a difference, right? So I would be surprised, but I've been surprised before. So the first thing that they're asking for is the difference. And that's not going to be difficult. Which you could do the answers to. Right. The second thing is they ask us is for this guy. That's going to require a fair amount of work. So here goes. Square root of 2.9 squared divided by 35 plus 2.1 squared divided by also 35. And the answer here is 0.61. roughly. And then they ask us for the approximate 95% confidence interval. Now, this is the generic formula for all confidence intervals, right? This guy we know is 2. This guy we know is 0.61. For an approximate 95%er, what do we use?
2.
So it's going to be 2 plus or minus 1.22. So it's going to be somewhere in the region of 0.78 all the way up to 3.22. And then I just looked and they wanted the answer to the nearest 10th. So I guess it's 0.8 to 3.2. And we were all proved wrong. Isn't that interval got nothing but positive numbers in it? Which means that X1 is bigger than X2, right? Men's heads are bigger than women's heads. I would still be very skeptical of that result. What's my problem?
Is it the size of sample size?
Yeah, I don't. You know, the process will generate answers, but a human being has to be at the back end of that and saying, okay, it does say that there's evidence, and there may well be true, right? I'm not saying it's not true, but I'm not happy with 35. I don't want to go to the bank and bet money on that one. Couldn't you easily get screwed? I mean, if you just pick randomly 35 people, can't you just sometimes have a really bad day and pick 35 of the weirdest shaped guys' heads you've ever seen in your life? And you don't even need 35 of them. Don't you only need 3 or 4 really massive heads, and that's probably enough to screw the answer up. Right. Sample sizes have to be done with as big a data set as you can. If you want to be safe, do 350, do 35,000. You know, if that data came out from a 35,000, then I would be saying, yeah, well, it's one of those physiological differences. We all know that men have bigger bones than women. We all know that men's, you know, whatever it is, you know, have more hair than women or less hair, whatever it should be, right? We can accept that because it's scientific. I do not, and I see it so many times in the news that it drives me crazy. It's some guy in Sweden does a survey and comes up with some really stupid result, and then they have a nice news article, and then it's a half-hour show on TV about it, and then 6 months later somebody in Japan says, well, we tried to do the same thing and we couldn't find what he's talking about. Right, what am I talking about? A Swedish study has discovered that people who eat a lot of carrots are getting far too high colon cancer. And then people start freaking out and not eating carrots because they don't want colon cancer. And then you find out the study was done with 30 people. And all you ended up with is 2 people with colon cancer. Well, couldn't you just get bad luck in 30 people and 2 of them that ate a lot of carrots had colon cancer, right? There is no connection. It's that kind of bad science that is prevalent today. And